So let's look at current gain. We said one of the important parameters of a bipolar transistor is the current gain. And we had seen this particular slide earlier, which shows the collector current, which is due to electrons injected into the base, which travel to the collector. And it shows several components of the base current. The base current has a component which is due to injection of holes into the emitter. So that part is there. And then another component is due to recombination of holes in the space charge region. And another component due to recombination of holes with the injected electrons here. Some of the electrons recombine here. So it is that component also. And as I was mentioning, there may be another, actually there is one more component which is due to the reverse bias current associated with this particular junction. And we'll assume that is small and we'll neglect that. Collector current, we have already seen. This electron current goes as IS exponent VB by VT minus 1, and we had derived this particular expression here. So IB is IB1 plus IB2 plus IB3, and we can then write IB by IC, which is the net beta, 1 over beta, and therefore one can define that beta has several components. One could define a beta 1 due to base component IB1, and similarly beta 2 due to IB2 and IB3 here. So the total net effective beta one can write as 1 over beta equal to 1 over beta 1 plus beta 2 plus beta 3 here. Whichever one is the smallest one will have a dominating effect on the overall current gain. So what we were doing was looking at each one of these components one at a time. So let's look at the first component, which is due to current injected into the emitter, the holes injected into the emitter. And okay, so we have this collector current here. So we were trying to get the expression for IB1, which we had obtained earlier during a derivation of Ebers-Moll model. We had shown that the base, this component here, which is due to injection of holes, is area Q, of course, minority carrier density here, Ni square over NdE. Diffusion, it's a diffusive current. So diffusion constant of holes divided by the distance over which the diffusion takes place here, which is emitter thickness here, and exponent VB by VT minus 1 here. And we take the ratio, and we, in this expression, note that what I have done is deliberately, even though both emitter and base are silicon, I've deliberately written Ni in the base, NiB square, and Ni in the emitter as Nie square here. Although both materials are silicon, we'll show you in a minute that doping has an effect on the effective band gap, and it changes Ni here. Okay, so that for that reason, because the doping is different in these two regions here, we have kept Ni also different in these two regions here. And therefore, if we take the ratio of these two quantities, we get the current gain, dN by dP, the ratio of the dopings, the ratio of the thicknesses, and NiB square over Ni square. And let's take an example and work out, get these numbers here. So for our discussion, what we'll do is we'll take a bipolar transistor that you see here. We'll take emitter thickness as 0.2, base thickness also as 0.2. So these are 0.2 are total thickness of the emitter, the total thickness over which I have n plus doping here. And similarly, this is the metallurgical thickness here of the base here, which is 0.2 micron. And collector right now is thick, so I'm not indicating, say, the collector thickness is about a micron. All right, so doping levels are N plus, emitter doping 5 times 10 power 19, base doping 5 times 17, collector doping 10 to the power 16. Okay, typical doping levels. And for, we'll assume that the lifetime, recombination lifetime everywhere is 1 microsecond. Lifetimes do vary depending on the doping, but for simplicity, we'll assume this here, 1 microsecond here. And so for once you have the doping levels, the mobilities are doping dependent, and therefore one can determine what the appropriate mobilities are. So for example, because it's heavily doped N plus here, the whole mobility is pretty small, 53.2 centimeters square volt per second here. So that's the whole mobility, and from the whole mobility one can get a diffusion constant. Similarly, the doping is moderate here. So we get an electron mobility of 346.5 here, and that gives us a diffusion constant of 9. Okay. And I've also given you so this is the doping of electrons. Okay, and this is the doping of holes in the base here. Note that doping of holes in the base is 214, right? But the same holes in emitter have a mobility of 53.2, all because of heavy doping here. And there's a lot of impurity scattering, and that's why the mobility is smaller here, 53.2 versus 214.2. Anyway, so the point is that once you know the doping levels, the mobilities have been extensively measured by people, and we have empirical expressions which tell us what to expect, what kind of mobility to expect for a particular kind of doping level. Yeah. So, and these are typical values that you would get here, dN and dP that you see here. And so what I'm going to do is, when I look at current gain, I'm of course looking at it in forward active. So I'm assuming emitter is ground. Base is about 0.8 volts, forward bias. Collector, so this is VC is, so it's not -2, collector voltage is +2 here. Okay, so collector is +2, and base is 0.8, and so collector base junction is reverse biased, and emitter base junction is forward biased here. Now, remember in our expression, if you go back and look at the current gain requires WE, which is the thickness of the neutral region here. WE is not the total emitter thickness, it's the thickness of the neutral region here. Okay, and similarly WB, we have said earlier, is the thickness of the neutral region here, WB. So in order to find that out, what we need to do is find out how much are these depletion regions here. Because what we have for us is this total thickness here, 0.2. Okay, and to find out what is the thickness of the neutral region WB, we have to find out what is this depletion width here and what is this depletion width here. So we have expressions for depletion width. I'm not going to go through it. One can determine the depletion width in the emitter or in the collector is 13.5 nanometer here. This extent of the depletion region in the base here, that's 13.5. In the emitter is 23.6 nanometer, and therefore the net effective base width will be equal to 0.2 micron, the metallurgical base width, minus the depletion widths in the emitter side and minus the depletion width in the collector side here, or this side and on this side here, and we get an effective base width which is 0.163. So note that you had designed for 0.2 micron, but the effective neutral base width is only 0.163. So it's significant. The difference between here and here is significant. Okay, you can't just assume effective base width equal to the total base thickness here. All right, so with that in mind, we use our expression for the current gain. Current gain due to what? Current gain due to the component because of injection of holes into the emitter here. And so dN by dP, we know now dN and dP here, ND by NA, WE by WB. Now note that what happened, WE here, because emitter is so heavily doped, 5 times 10 power 19 compared to 5 times 17, so it's 100 times more heavily doped compared to the base. So the depletion region in emitter is negligible. This XNE that you see here is negligible. So emitter width is practically equal to 0.2 micron. Okay, so we have taken that as 0.2 micron. So this is 0.2, this is 0.163, and therefore if we multiply them, all of them together, the factor is 6.5. This is ND by NA is 100. WE by WB is 1.23. And right now, I'm just assuming that because the material is the same, silicon here, for the moment, that the Ni is the same in both the regions here. So it's 1. And if you multiply them together, you get a value of 800. So you get a current gain due to the component of holes injected into the emitter as 800 here. Now, note where this 800 value is coming from. A significant fraction is coming from here, dN by dP. The fact that it's the electrons which carry the collector current, and dN is significantly higher than dP, so 6.5. Another major contribution is coming from the fact that emitter doping is so much higher compared to base doping here. This is the most significant factor here, and this is relatively minor here. Okay, WE by WB is okay. It's not too large here. So you get a current gain of 800. This is what this prediction is. Now, this current gain, if you actually go and make a transistor like this, you will not get 800. You'll not get 800 because, as I've hinted earlier, the Ni, when you dope heavily, the Ni in this region becomes different from Ni in this particular region. Ni is doping dependent. And let me show you one particular paper, an early paper in 1976, which is talking about the PN product in silicon. PN product is what? P into N at equilibrium is Ni square. So what this person is talking about is Ni square. And basically what is being talked about is that when you put doping, the doping causes perturbation in the crystal structure. And it results in decrease in the effective band gap. Okay. And so what is happening is, if you go and look at this particular picture here, focus on this particular picture. So this diagram shows you so we are considering a p-type semiconductor here for a mobility of 10 power 15, and this is for a mobility of 10 power 19. Okay. Now note what is happening. Let's look at this particular picture here. Several things are being plotted here. So let's focus on 10 power 15 case here. This is the density of states. Density of states are here, and then, because I have a forbidden gap here, so density of states becomes equal to 0 here in this entire region here. Okay. So density of states goes like this, and then I have valence band density of states, which goes here, this part here. Okay. Remember, these density of states were going as square root E. If you recall, density of states had that particular one, right? So this is density of states. And when you take density of states and you integrate it with Fermi-Dirac, you get electron density and all that here. So that's showing number of carriers here. And that's showing number of holes here. Number of holes, how they're distributed in the energy band here. And so obviously it's p-type, so I have more number of holes as compared to whatever here. And then it's also showing you that because of, I've doped the p-type, there is a acceptor impurity here, right? So there are states here. There are energy states in the band gap. Why? Because of the dopant here. We have introduced dopant, and we know dopants introduce energy states within the energy gap here. So that's the thing. All right. So that's the picture that you're familiar with. Dopants introduce traps, or dopants introduce energy state very close to the valence band. This is what is here. And there are holes here. There are electrons here. That's the density of states. Now, when you increase the doping, now come to the lower part here. When you increase the doping to 10 to the power 19, several things are happening. Note first, you can clearly see an impurity level and you can see a valence band, right? You can't see an impurity level and you can't see a valence band separately. What has happened is, when you add a lot of impurities, one impurity level starts interacting with the other impurity level. The average separation between two impurity levels decreases once the concentration increases. And these impurity levels then, instead of being a discrete level, they broaden into a sort of band. And we call it impurity band. Just like, remember, ordinary is in a silicon, if you have one silicon atom, you have one level, discrete levels are there. And when you make a crystal, the discrete levels, they interact with each other and you get a band. So similarly, you're getting an impurity band here. And the impurity band, band means it spreads out in energy here. And it also causes a distortion in the valence band here. See, when you add a lot of impurities, the impurity atoms have a different size as compared to silicon atoms, right? They have a different size there. And therefore, you can imagine that different size means you are going to create stress or strain in your lattice there, right? And stress and strain and pressure, they distort the lattice and thereby they affect the band gap also. So what is happening is, note that as a result of all this, this impurity has expanded. The valence band has spread out. There is a tail in the valence band here, and they've all merged together. And density of states, note that density of states is looking like this. And there's a distortion in the conduction band also. Note that conduction band, if you see here, density of states is still here, and here density of states. So there's a distortion in the conduction band also. In effect, what is happening is, if you look at the energy gap is 1.121 here, and energy gap has become 1.036 here. So effective energy gap, the place where conduction band density of states goes to 0, and the place where total density of states associated with, now there's no distinct impurity level here, it is all merged, and the place where the effective valence band density of states goes to 0 here, and you start looking at the difference here. the energy gap effectively has reduced. And the moment the energy gap reduces, the Ni changes. So this is a very important phenomena that occurs as you add dopants. Okay. And there's people have measured these band gap narrowing, and this is an empirical expression that is commonly used, which describes how much does the band gap narrow. What is the decrease in the energy gap as you add dopants here? Let's say, so N refers to the doping density. So this equation is valid only when N is larger than 10 to the power 17. Below 10 to the power 17, band gap narrowing is negligible. You can assume as a normal band gap. So if you use 9 into 10 power minus 3 ln n by 10 power 17, so it's an empirical expression which fits the experimental data. So now what you can do is you can take whatever doping level you have, you plug it here, and you get what is the amount by which the band gap is reduced. Okay, and as an example, we had doping in the emitter 5 times 19. So if I plug 5 times 19 here, I find that my band gap has decreased by an amount 0.112. So band gap in the emitter has reduced by this much value here. And if band gap reduces by this much value here, note that Ni goes as exponential with the Eg by 2kT here. So my Ni compared to my normal Ni has increased by a factor of 8.65. So because of this band gap narrowing, the Ni in my emitter is higher than my normal Ni in silicon by a factor of 8.65. So that's in the emitter. Similarly, if I calculate in the base I have a moderate doping 5 times 17. So 5 times 17, if I calculate, I get a delta Eg of only 30 milli electron volt. And Ni in the base is also higher, but not by much, it's 1.8. Okay, so now this is a factor. This is what I was telling you, that Ni in the emitter is different from Ni in the base. Why? Because the dopings are different, and the doping caused band gap narrowing. And therefore, my effective band gaps in the emitter and the base are different, which results in Ni in the emitter being significantly higher compared to Ni in the base. So now, if I look at these two, Ni B square by Ni E square, the Ni in the base divided by Ni in the emitter and whole square turns out to be 0.043. So now if I go back to my gain, note that I was saying gain is NIB square over NIE square. So this was the factors that I had written out earlier, 6.5, 100, 1.23. They were giving me a value of 800. But then band gap narrowing, once I take band gap narrowing into account, it gives me a gain of 34.4. So you can see the importance of this particular phenomena here, band gap narrowing here. If you don't take band gap narrowing, you would expect a gain of 800, right? You go and make a bipolar transistor with that doping and you measure 34 or 35. All that is occurring because of this extremely important phenomena of band gap narrowing, that the band gap in the emitter is significantly smaller than band gap in the base. All right. So this says that, if I look into this expression here, this says that, if you increase the doping, emitter doping, you get increase in gain. But note that, yes, this expression tells you that as you increase the doping, you get increase in gain. But as you increase the doping, what happens? Band gap in the emitter narrows. And as it narrows, Ni square increases here. Right? So you don't get that much advantage of increasing the doping in the emitter because of Ni here. So as you increase doping, Ni also increases here. So it sort of negates the effect of higher emitter doping here. So beta 1 for us then has become a fairly small value, 34.4. All right, value here. Okay, so that's the current gain due to the holes injected into the emitter. Let's look at current gain now due to other components here. All right, so before we leave this particular topic of this beta 1, there's a concept that you will often hear in bipolar transistor, which is called emitter injection efficiency. The idea here is that, note that the entire, in a bipolar transistor, the collector current comes because of the electrons here, and the base current comes because of the holes here, right? And you want emitter to be efficient in terms of injecting electrons. You don't want a lot of holes to be injected into the emitter here, because that contributes to base current and that contributes to lower beta here. So the emitter injection efficiency, it means how efficient is my emitter in injecting holes in injecting electrons as compared to the holes here. So emitter injection efficiency is then defined as IN, the electron current injected, divided by the total current associated with the emitter, which is IN plus IP here. In this expression, we are neglecting 2 and 3. We'll see that components 2 and 3 are small. Okay. So emitter injection efficiency IN divided by IN plus IP. So the electron current divided by total current associated with the emitter here. And it's easy to see that I can now take a ratio IN by IP plus 1 here. And this is what we have defined as beta 1. The ratio of component 1 and this one is beta 1 here. So, the emitter injection efficiency is related to our beta 1 factor here. Okay. So emitter injection, we have already calculated beta 1. And if I plug the expression for the value for beta 1, we get an emitter injection efficiency of 0.972. Okay. So obviously, for getting high current gain, what you're looking for is emitter injection efficiency to be as high as possible. You want IN to be much, much larger than IP here. So you want this value to go to as close as possible to 1 here. In our case, is not very good. 0.972 is not very good. One is looking for 0.99, and higher here. All right. So let's look at now the next component of the. Okay. All right. So there's one more issue here. And the issue here, so emitter injection efficiency. What I've when I'm showing you the current, base current, and the current gain, note that the current injected into the emitter, the holes injected into the emitter, we had used an expression like this, that the hole current injected is equal to it's a diffusive current. So that's why you have QA dP here, and you have excess hole density here, which is delta P0. This is the thickness here, WE. And we assume that this is an ideal contact. And at the ideal contact, the excess hole density is 0 here. So that's why delta P0 minus 0 divided by W here. So that's how we get the hole current injected into the emitter here. Now you can imagine that you want to get larger current gain. And if larger current gain means 2 ways of getting it. You either increase the electron current injected into the emitter, or you decrease the hole current injected into the emitter here. So hole current is here. So now the issue is, how can I decrease the hole current? Well, QA, dP are constants here. Delta P0, I don't have control because delta P0 depends on the applied bias and the doping. So the effect of doping we've already seen. Thickness, of course, I can increase and decrease, so that is under my control. Now, here, what you see here is 0. 0 is because the contact has been assumed to be ideal. Now, you can play around with the contact property. You can make a contact such that the excess carrier density at the contact is not 0. Deliberately, you can do those things. So it's not 0. So note that if you could do that, so it's not an ideal contact where carrier density goes to 0. If you could do that the carrier density is not 0, then you note that you can affect the slope here. You can affect the slope here, and therefore you can get smaller base current. And smaller base current will translate into a higher current gain. So you can, for example, I'm not going to go into the details. So in an emitter, most bipolar transistors, silicon bipolar transistors have a polysilicon here, polysilicon emitter. The goals are to alter the properties at the emitter contact and emitter here, such that the carrier density doesn't go to 0, but carrier density is finite here. So one can alter the amount of current that is injected into the emitter by altering the contact property here. Okay, so I just wanted to tell you that one can play around with this factor here also. It need not be 0; it can be a non-zero quantity by altering the contact properties here. All right. Okay, so let's come back to the current component number 2. Current component number 3. Okay, so next is beta 3. So we've looked at beta 1. Beta 3 is this component here. So IC divided by IB3, and IB3 does what? It supplies any holes which are needed to replace the holes which are lost due to recombination. So as the electrons are injected here, some may recombine with the holes, and component number 3 goes and replaces those holes which are lost here. All right. So that again IC expression is we know. So we have to obtain an expression for IB3 here. So note that IB3 then, according to what we just said, will be equal to whatever is the current injected here, IN2 minus IN3, right? Current injected at the emitter side minus the current reaches this end. The difference of the two has to be equal to the electrons which are lost due to recombination, and which is same as the holes which are lost due to recombination here. So IB3 is the difference of these two, IN2 minus IN3 here. Now, how do I determine this? Well, let's go back to our continuity equation. Continuity equation in steady state. So del N by del T is 0. This is my current term here. There's no generation. And recombination is delta N by tau N. So that's my continuity equation. So now remember, I have to get IN2 minus IN3. So what it says is just integrate this. So we get del IN by del X is QA delta N by tau N. Right? So this equation comes here, and then you integrate from x2 to x3, and therefore you get IB3, which is IN2 minus IN3. So as you integrate that, you get IN2 minus IN3. QA tau N comes here, and basically integral of delta N from x2 to x3. So all I need to do is integrate my charge from here to here, and from there I will get the IB3 here. Okay, so that's how one gets that. Okay. Now, this is where a little bit one can do this problem exactly, but I'm doing it through an approximation. So what we are saying is that recombination is very small in this region here. Is there, but it's very small. And therefore, note that, so del IN by del X is QA delta N by tau N. So recombination is small and current is diffusive. So I can write IN is QA dN del N by del X here. So what we are saying is to calculate the electron density profile. To calculate the electron density profile, I can assume IN to be constant to get delta NX. Okay, why? Because the recombination is very small, and if recombination is very small, then IN is practically constant here, and therefore, if IN is constant, then del N by del X is here constant here. Okay, and then so this is the picture here. Note that it's not going to be exactly linear because we know that IN is varying. IN will vary, so delta NX will not be exactly linear, will have a small slope, but the changes are going to be negligible. Okay, the changes are going to be negligible, and therefore it's a good approximation to think of it as linear. Okay, so once you think of it as linear, then my base current QA, note that base current was QA tau N and the integral of delta NX. So integral of delta NX now is simple QA tau N here. Integral is nothing but half, is the area under the this graph here, half delta N0 multiplied by the effective base width, which is WB. So that's how we end up with getting a expression for IB3. Now note that delta N0 I know. What is the electron density injected at this particular point here? So we know this, and therefore we can write down what is IB3. Okay, and of course IC is also the same, QA dN delta N0 by WB. According to this expression here, IC is here, right? So you may be wondering that, I'm calculating the base current here. I'm saying IN2 minus IN3, IN2 and IN3 are different to obtain this particular expression. But then at another place, I'm saying the carrier density is linear, assuming IN is constant here, right? So, you make different assumptions at different places to simplify your analysis here. So anyway, so IC is here, and now what we do is we take the ratio of the two, ratio of IC, and we take a ratio of IB3, and we get beta 3 equal to 2 dN tau N by WB square, simple expression. dN tau N is nothing but diffusion length square, so we get beta 3 equal to 2 ln by WB square. And if I plug in my values, the values that we had for dN was 9, tau N was 1 microsecond here, and diffusion length then turns out to be 30 micron. Our base width is 0.2. In fact, effective base width is 0.16 here, and we now put in all the numbers here. Beta 3 turns out to be very high, 6.8 into 10 to the power 4, right? So extremely high value of beta 3, which means what? That basically the number of electrons which are recombining in the base are very, very small. And therefore, the component number 3 is extremely large. So 1 over beta is 1 over beta 1 plus 1 over beta 2 plus 1 over beta 3. Beta 1 we have already calculated 34.4. Beta 2 we still have to calculate. Beta 3 6.8 into 10 power 4 is not going to matter. It's not going to determine what is your current gain. The current gain will be, according to the present picture, will be determined by these two terms here, rather than this one. Okay. So coming back again, we said that in principle there is a component here, number 3, which replaces the electrons which recombine here, but this component is very, very small. Okay, so it is very, very small. And now there can be cases, you can imagine there can be cases where this factor becomes large. If you look at beta 3 is 2 ln by WB square. So if you were to make your base very, very thick for some reason, right? If you make the base very thick, then this number could come down. Okay, but as I said, in most modern bipolar transistors, we keep the base width fairly narrow, and therefore this component is not an important factor. All right, so again, related to this component of associated with 3, there is a factor that we call as base transport factor. Now, base transport factor by definition is IN3, this component, divided by the component here, IN2. And I guess it makes sense to call it base transport factor because, what do you want? You want all the electrons that are injected here, you want them to reach to the collector here, right? And you don't want any electron that is injected to be lost in the base here because that gives rise to collector current. You want to maximize collector current. So IN3 by IN2. IN3 is what reaches here. IN2 is what is injected here. So the ratio is what we call as base transport factor, right? How many electrons are lost in the transport process, right? So IN3 by IN2. Of course, you want this factor to be close to 1. And it's related to our, obviously, beta 3 here. So, one can easily show alpha T is 1 minus IB3 by IC. So 1 minus 0.5 WB by LS square. Okay. So alpha T is here. And so alpha T is very, very close to 1 here for our case because the beta 3 is very high. So base transport factor is practically 1. All the electrons that are injected, they reach the collector end. So that's our component number 3, right? That then brings us to component number 2. And component number 2, we are saying the holes which are injected here, some of them recombine in the space charge region here. So that's related to what we call as base-emitter space charge recombination. It's a recombination current. Okay. So beta 3 is IC, beta 2 is IC by IB2. IC again is the same expression. IB2 now, we use our expression from a diode. For a diode, we had calculated space charge recombination. And this is the expression that we had obtained. QA, this one, Ni by 2 tau refers to the net generation rate within the, or net recombination rate within the Ni by 2 tau times exponent QV by 2 kT refers to the net recombination rate inside the depletion region. And this is the effective width over recombination occurs here. So that's the expression that we have derived. And the same expression we'll use over here to calculate what is the base current here. And so it's a little bit complicated expression, conceptually simple, but there are several terms here. So one can take the ratio and get an expression for current gain due to the component number 2. Now, the important point is, note that other current components, when I looked at IB1 was going as exponent QVB by KT. When I looked at IB3, it was also going as exponent QVB by KT. So when I took the ratios of collector current and IB1 or collector current and IB3, the current gains came out to be independent of bias. They came out to be independent of bias. This is different now. This is one of the key characteristics of this component here. Recombination within the space charge region goes as QVB by 2 KT. So when I take the ratio of collector current, which goes as VB by VT, and this goes as QVB by 2 KT, I end up getting a current gain which is bias dependent. I get QVB by 2 KT. right? So I get this now beta 2, which is now current dependent. And note, if I look at, so all this prefactor term is there, we can evaluate once we know the doping, lifetimes and all of that, we can evaluate that. But beta 2, if you look at this exponent QVB by 2KT, note that I can write now beta 2 goes as square root JC, current density, collector current density. This is very, very important. That beta 2, the space charge recombination current gain associated with it, goes as square root of this. Why? This is exponent QVB by KT. Collector current also goes as exponent VB by VT. So if I take square root of collector current, what will it be? Exponent VB by 2 VT. And that's the term that I'm saying, that beta, the space charge recombination, is square root JC. Right? So at low currents here, you will find beta 2 can become very small. While at higher currents, then beta 2 will be very large and maybe negligible. So this is pointing out that space charge recombination will become dominant at lower currents and can cause problem for us. Okay. All right. So now if we evaluate at 0.8 volt, we are evaluating all the current gains at around 0.8 volts, which is fairly large voltage here, 0.8 volt. And if I plug in all the values here, I find beta 2 is 7 times 10 to the power 5. Very high at that value. Right? But note, it's very sensitive to VBE, right? Exponentially dependent on VBE. So as I reduce VBE, now this beta 2 is going to drop sharply, right? So, and if you make it fairly small, then beta 2 can become very, very small and can become a limiting factor, right? So this is the characteristics of the space charge recombination current. It depends on the bias here, and therefore it depends on the collector current density. So if we put all the terms together, beta 1 for us was 34.4, beta 2 is 7 times 10 power 5, beta 3 is 6.8 into 10 power 4. Well, it's dominated by beta 1. So when you are when reasonable currents are flowing in your collector, in your bipolar transistor, voltages are reasonably high, current densities are high, the base current is dominated by injection into the emitter. And this is what determines the current gain, beta 1 factor here. Okay. And this is fairly small, 34.4 for us. Of course, one can alter the base doping, one can change the thicknesses here, and instead of 34.4, we can get, 70, 80, 100, 200. That's all part of the design of a bipolar transistor. All right, let me show you now. Let's see whether with all this background, we can understand the current gain for a actual bipolar transistor. 2N222 is a very popular transistor, NPN transistor. This is the current gain versus collector current plot for experimentally measured plot. This is how current gain goes. And the current gain is plotted as a function of collector current and also as a function of temperature. So can we understand now the behavior? What is happening current gain here? Let's take the room temperature first. Room temperature, what we are finding is current gain is starting and increasing. Do we expect that? That current gain will be lower at lower collector current, and then as you increase the collector current gain increases. All right, let's look at the qualitatively. Current gain increases as you increase the collector current initially. Why? Can we understand that? Look at all the factors here of that we just looked at. Beta 1 independent of, there's no this thing here. Beta 2, what did we say? Beta 2 goes as square root of IC. So this is the component that actually increases with collector current. This component beta 2 goes as square root of IC, and this is also independent, and anyway it's very large, so it doesn't really matter. So now think of your current gain in a bipolar transistor being determined by two factors here, beta 1 and beta 2. Beta 1 is constant, right? And beta 2 is what is current dependent here. So as you increase the collector current, this component increases here. So this is what is causing this factor. It's increasing because this factor is increasing. So it has a role to play here, and it is in this transistor is is significant to cause this small change here, this increase here. Okay. So whenever you see current gain increasing with collector current, a dominant factor is this particular term here, beta 2, space charge recombination. All right, so that's the first thing. So we know now why it is increasing. Why is the current gain dropping as you reduce the temperature? Can we understand that? As you cool your transistor down from 25 to minus 55, the current gain is dropping. Why is that? What is the dominant factor? Again, go back here and look at this one picture here. Why is the current gain dropping? Note that only two factors are important, beta 1 and beta 2. Right? Why is the current gain dropping? And it's dropping very significantly. Right? Very significant drop. From 25 to note here is very large drop here. Why? What is the reason? What is dropping? Note that beta 2 has an effect, but the dominant beta is determined by what? Beta 1. And where is the temperature dependent term? Here. This is the temperature dependent term. Band gap of emitter is lower than band gap of base. So this term is actually negative. Exponent minus this term is negative here. So as you raise the temperature or as you decrease the temperature, this term becomes smaller. So it's because of this band gap narrowing that you see here. This is the dominant temperature term. There may be small temperature terms here in terms of mobility and all of that, but this is the dominant factor here. Okay, and this is what is causing my current gain to drop here. Now this is problematic because many times for some application, you may want to operate your transistor at very low temperatures. Let's say liquid nitrogen temperature, which is 77 Kelvin. Now if you go to 77 Kelvin, the current gain according to this may become negligible. You won't get a current gain at that particular point here. All right. So you can't go to very low temperatures and have a bipolar transistor work because the current gain may become very, very small here. So this is an important point. And as your bipolar transistor heats up, the current gain actually goes up here. Right. So this is a behavior, when you're designing circuits and all that, you have to be aware of. The gain is going to go up with increase in temperature, or gain is going to go down with decrease in temperature. And the reasons are here. Reasons are this particular factor. Okay. One last feature that you note in this particular diagram. So we know now why it is increasing because of space charge recombination term, which increases, gain due to that increases. Why it is temperature dependent, we know. But there's another thing that you see here is that as you keep on increasing current density, a stage comes when it starts dropping sharply. So when you go to sufficiently high current densities, the gain begins to drop very rapidly. So what it is telling you is that there is an upper limit to a collector current at which you can operate your transistor. If you go beyond, if your design depends on a current gain of around, let's say 200 or so, and then if you go beyond, let's say 100, then, the current gain is falling, fairly rapidly. So that's something to be aware of. And where does it come from? Well, it comes from here. So the current gain then depends on primarily, as I said, when you go to high bias, the current gain depends only on beta 1, the first term. Beta 1 is a ratio of this current and the current injected into the emitter here, right? So IC is here and IB is here. Now we are talking about high, when you apply high bias. Now when you apply high bias, if you look at collector current, the collector current, the way it is written is AQ, diffusion constant divided by W, and Ni square over Na exponent VB by Vt is what? Is the carrier density injected into the base here. Is the carriers which are injected into the base. Ni square over NDE, this part is the carriers which are injected into the emitter. And of course, it's a diffusive current, so diffusion constant divided by WB. Now, as you keep on increasing VBE, the excess carrier density in the base keeps on increasing. Eventually, what happens is the excess carrier density starts becoming comparable to the doping. There's a doping in the base, which is Na. So now, when it starts becoming comparable, minority carriers are no longer minority. They're becoming comparable to the majority carrier concentration. And now what happens is IC now no longer goes as this, VB by VT. because our whole derivation was based on that it's a minority carrier current and low level injection where the injected carrier density is much smaller than the majority carrier. But as you keep on increasing the bias, the minority carrier concentration starts becoming comparable to majority. And in that case, I'm not showing you, but what happens is that IC begins to go as not VB by VT, but VB by 2VT. Carrier density now no longer increases as VB by VT. Actually, there's a simple derivation I'll show you sometime that injected carrier density doesn't go as VB by VT, but VB by 2VT. So IC now no longer increases as rapidly. IC starts showing a curve. It starts to saturate. But note that high level injection begins to occur here. High level injection means injected carrier density starts becoming comparable to doping. But look at the emitter side. Emitter side, you are also injecting holes, but high level injection will not occur into the emitter. Why? See, this is the carriers which are injected into the emitter. Why? Because the emitter doping is so high. So high level injection does not occur into the emitter because its doping is very high. The injected minority carrier density is very low, much lower as compared to injected minority carrier density here. So no high level injection occurs here, while high level injection occurs here. So IC begins to go as VB by 2VT, and this component continues as VB by VT. And therefore now what you will get is beta 1. If this becomes VB by 2VT and this remains VB by VT, beta 1 starts going as exponent minus VB by 2VT. And exponent VB by 2VT is nothing but IC. So beta 1 starts going as 1 over IC, starts dropping. Starts to drop with increase in bias. Okay. So this is the trouble that occurs as you go to higher biases here. So we see here the current in this beginning to drop here. So in all bipolar transistors that you will see here, the current gain, this current gain slightly increasing, you may or may not see depending on the importance of space charge recombination. In many cases, you may see relatively flat current gain, but then as you go to higher current density, you find a sharp drop. And the sharp drop is occurring because of this factor here. High level injection occurring into the base here, which makes the current goes as VB by 2VT, and then makes the current gain goes as 1 over IC. Okay. So let's stop here. Tomorrow we'll look at base fit modulation early effect here.